Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast emptiness of interstellar space, two human-made objects continue their eternal voyage. Launched in 1977, NASA's Voyager 1 and Voyager 2 have traveled farther than any other craft in history. For nearly half a century, these twin explorers have been our ambassadors to the cosmos, pushing the boundaries of human reach beyond our solar system. The Voyager missions began as an ambitious plan to take advantage of a rare planetary alignment that occurs only once every 175 years. This Grand Tour configuration allowed the spacecraft to use gravitational assists, essentially cosmic slingshots, to visit all four outer planets with minimal fuel consumption. What started as a 4-year mission to study Jupiter and Saturn evolved into an unprecedented journey that continues to this day. Voyager 1, the faster of the pair, is currently over 14 billion miles from Earth, while Voyager 2 trails at nearly 12 billion miles. At these distances, radio signals traveling at the speed of light take approximately 21 hours to reach Voyager 1 and 17 hours to reach Voyager 2, a testament to the sheer scale of their journey. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The Voyager spacecraft represent the pinnacle of 1970s technology, yet they continue to function with less computing power than a modern smartphone. Each Voyager carries 3 radioisotope thermoelectric generators, or RTGs, which convert heat from the natural decay of plutonium-238 into electricity. This ingenious power solution has kept the probes operational far beyond their expected lifespan, though their power supply diminishes by approximately 4 watts per year. In 2012, Voyager 1 made history by becoming the first human-made object to enter interstellar space, the region beyond the heliosphere, where the solar wind's influence gives way to the interstellar medium. Voyager 2 followed suit in 2018. These transitions marked the beginning of a new phase in their mission, the Voyager Interstellar Mission, or VIM, focused on studying the boundary between our solar system and interstellar space. The heliosphere acts as a protective bubble around our solar system, created by the solar wind, a constant stream of charged particles flowing outward from the Sun at speeds of around 1 million miles per hour. This bubble shields us from cosmic radiation and interstellar particles. The boundary where the solar wind's pressure balances with the pressure of the interstellar medium is called the heliopause, and crossing this threshold was a momentous achievement for both spacecraft. As they journey through interstellar space, the Voyagers continue to send back valuable data about this unexplored region. They've revealed that the boundary between our solar system and the rest of the galaxy is more complex and dynamic than previously thought. They've measured the density of the interstellar medium, detected interstellar magnetic fields, and observed cosmic rays from distant stars. Each bit of information helps scientists understand our place in the galaxy and the nature of the protective shield that surrounds our solar system. Despite their remarkable longevity, the Voyager's mission will eventually come to an end, but their journey won't stop there. They will continue their silent voyage through the Milky Way for billions of years, carrying with them a message from humanity, the Golden Record. Affixed to the side of each Voyager spacecraft is a 12-inch gold-plated copper disc, a time capsule intended for any intelligent extraterrestrial life that might encounter these wanderers in the distant future. The Golden Record, as it's known, represents one of humanity's most ambitious attempts at interstellar communication, a greeting card from Earth, designed to last at least 1 billion years. Curated by a committee chaired by renowned astronomer Carl Sagan, the record contains 115 images encoded in analog form, a variety of natural sounds from Earth, like waves breaking on shore, thunder, and birdsong, as well as musical selections representing diverse human cultures and spoken greetings in 55 different languages. The first message, in English, simply states, "Hello from the children of planet Earth." The record's aluminum cover is electroplated, with uranium-238, which has a half-life of 4.5 billion years. As this material decays, it provides a radioactive clock that could help finder civilizations determine when the Voyagers were launched. The cover also features an ultra-pure sample of carbon-14 to serve as an additional time marker due to its 14,000-year half-life. Perhaps most remarkably, the cover includes a diagram explaining how to play the record and extract its contents, similar to the instructions one might include with a gift to a distant friend. There's also a pulsar map showing the location of our Sun relative to 14 pulsating neutron stars, cosmic lighthouses whose precise rotational periods could help an alien civilization pinpoint Earth's location in both space and time. The musical selections on the Golden Record represent a cross-section of world cultures, including works by Bach, Beethoven, and Mozart, alongside traditional music from countries like Peru, Japan, and Senegal. Chuck Berry's Johnny B. Good represents rock and roll, while blind Bulgarian folk singer Valja Balkanska's haunting performance of Izlel je Delio Hajdutin soars as one of the most otherworldly pieces in the collection. The decision about what to include on the Golden Records sparked interesting debates among the selection committee. Sagan had initially wanted to include images of a nude human couple to accurately represent our species, but NASA ultimately decided against this, concerned about potential public controversy. Instead, the record includes an anatomical diagram of a male and female human, along with information about our DNA structure, human reproduction, and our planet's position in the solar system. Some have questioned the value of sending these messages into space. The odds of another civilization finding either Voyager are astronomically small. In roughly 40,000 years, Voyager 1 will pass within 1.6 light-years of the star AC 793888 in the constellation Camelopardalis. Voyager 2 will approach the star Sirius in approximately 296,000 years. And even if found, would an alien civilization have the technology or the desire to decipher our message? Yet the Golden Records were never solely about communicating with extraterrestrial intelligence. They also serve as a reflection of humanity's place in the cosmos, a symbolic gesture that transcends practical considerations. As Carl Sagan eloquently put it, the spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. In essence, the Golden Records represent an act of cosmic optimism, a belief that not only might we not be alone in the universe, but that we might someday be able to communicate with our cosmic neighbors. They are time capsules cast adrift on an interstellar ocean, carrying the sounds, images, and feelings of a small blue planet to the stars. Before venturing into the uncharted waters of interstellar space, the Voyager spacecraft completed their primary mission, an unprecedented grand tour of the outer solar system, taking advantage of a rare planetary alignment that occurs only once. Every 175 years, these robotic explorers revealed worlds that had previously been little more than fuzzy disks in even the most powerful telescopes. Voyager 1's closest approach to Jupiter occurred in March 1979, passing within 277,000 kilometers of the giant planet's cloud tops. The spacecraft's instruments detected Jupiter's complex weather systems, including the Great Red Spot, a massive storm that has been raging for at least 400 years. Voyager discovered that this storm rotates counterclockwise with a period of about 6 days and measured wind speeds of up to 400 kilometers per hour at its edges. Perhaps most surprising were Voyager's observations of Jupiter's moons. Io, the innermost of the 4 Galilean satellites, revealed itself as the most volcanically active body in the solar system. Voyager 1 captured the first images of volcanic plumes erupting from Io's surface, with material being ejected up to 280 kilometers above the Moon. Scientists later determined that these eruptions are driven by tidal heating. Jupiter's enormous gravitational pull flexes Io's interior, generating tremendous heat through friction. Europa, the second Galilean moon, presented a stark contrast to Io. Its surface appeared remarkably smooth, covered in a network of cracks reminiscent of sea ice on Earth. These observations led to the hypothesis that Europa might harbor a subsurface ocean of liquid water beneath its icy crust, a theory that subsequent missions have strengthened. Today, Europa is considered one of the most promising places to search for extraterrestrial life in our solar system. Voyager, one's encounter with Saturn came in November 1980, with the spacecraft passing approximately 124,000 kilometers from the planet's cloud tops. While Saturn's rings had been observed from Earth since Galileo's time, Voyager revealed their true complexity. Thousands of individual ringlets with intricate structures including waves, braids, and spokes. The spacecraft discovered several new moons and observed the bizarre hexagonal cloud pattern surrounding Saturn's north pole, a six-sided jet stream with each side measuring about 13,000 kilometers in length. After completing its Saturn flyby, Voyager 1's trajectory took it northward out of the ecliptic plane, the relatively flat region where most planets orbit. This path meant the end of planetary encounters for Voyager 1, but its twin would continue the grand tour. Voyager 2 visited Jupiter in July 1979 and Saturn in August 1981, providing complementary observations to those of Voyager 1. But its journey was just half complete. In January 1986, Voyager 2 became the first spacecraft to visit Uranus, passing within 81,000 kilometers of the ice giant's cloud tops. Uranus presented a stark contrast to the visually dynamic Jupiter and Saturn. Its atmosphere appeared as a featureless blue-green sphere, with few visible cloud features. Voyager discovered 10 new moons orbiting Uranus and revealed that its larger moons had been subjected to intense geological activity. Perhaps most striking was the discovery that Uranus rotates on its side. Its axis of rotation lies nearly parallel to its orbital plane, likely the result of a massive collision early in the solar system's history. Voyager 2's final planetary encounter came in August 1989 when it flew by Neptune, passing within 5,000 kilometers of the planet's north pole. Despite being 30 times farther from the Sun than Earth, Neptune revealed itself as a dynamically active world. Voyager observed the Great Dark Spot, a storm system comparable in size to Earth, and measured the fastest winds in the solar system, up to 2,100 kilometers per hour. The transition from our solar system into true interstellar space represented the most significant milestone in the Voyager's extended mission. This boundary, called the heliopause, marks where the influence of our Sun gives way to the interstellar medium, the diffuse gas, dust, and radiation that fill the space between stars. The journey to the heliopause took decades, with Voyager 1 and Voyager 2 traveling through a region called the heliosheath, the turbulent outer layer of the heliosphere, where the solar wind is slowed by the pressure of interstellar space. This region, first encountered by Voyager 1 in 2004, proved to be larger and more complex than scientists had anticipated. For 8 years, Voyager 1 traversed this transitional zone, with its instruments detecting increasing instability in the surrounding environment. The solar wind's speed dropped to zero, and the magnetic field lines became scrambled. However, the definitive evidence of crossing into interstellar space came on August 25, 2012, though scientists didn't confirm this historic transition until 2013, after carefully analyzing the data. The key indicator came from Voyager 1's plasma wave instrument, which detected the density of electrons in the surrounding environment. In interstellar space, this density is significantly higher than within the heliosphere. A fortuitous solar eruption in March 2012 sent a pressure wave that reached Voyager 1 about 13 months later, causing the plasma around the spacecraft to vibrate. By measuring these oscillations, scientists confirmed that Voyager 1 was surrounded by the much denser plasma of interstellar space. Voyager 2 followed its sibling into interstellar space on November 5, 2018. Unlike its twin, Voyager 2 carries a working plasma science instrument that directly measures the speed, density, temperature, pressure, and flux of the solar wind. This allowed for more immediate confirmation of its crossing. The instrument detected a sharp decline in solar particles and a corresponding increase in galactic cosmic rays, providing unambiguous evidence that Voyager 2 had crossed the heliopause. What the Voyagers found at this boundary has revolutionized our understanding of our solar system's interaction with interstellar space. Rather than a clean, sharp edge, the heliopause proved to be a complex dynamic boundary. The spacecraft detected unexpected magnetic bubbles where the interstellar magnetic field connects with the solar magnetic field, creating regions of accelerated particle exchange. Both spacecraft have observed that the interstellar magnetic field drapes around our heliosphere, distorting its shape. Instead of the symmetrical bubble scientists once envisioned, data from the Voyagers suggest our heliosphere may be more compressed on one side, possibly resembling a blunt bullet shape as our solar system moves through the interstellar medium at approximately 52,000 miles per hour. Perhaps most surprisingly, the Voyagers revealed that our heliosphere doesn't entirely shield us from galactic cosmic rays. High-energy particles accelerated by distant supernovae and other cosmic events. Some of these rays penetrate the heliopause and Helios heath, though their intensity increases dramatically outside the heliosphere. Understanding this boundary is crucial for future human exploration beyond our solar system, as cosmic rays pose significant radiation hazards to both spacecraft electronics and human health. The Voyagers also discovered a previously unknown magnetic highway at the outer edges of the heliosphere, where charged particles from inside the solar system can escape and cosmic rays from interstellar space can enter. This region acts as a porous membrane rather than an impermeable barrier. As they continue their journey into interstellar space, both spacecraft have detected the increasing influence of the interstellar medium. The density of charged particles has continued to rise, and the direction of the magnetic field has shifted to align with what astronomers predict for this region of the galaxy. The Voyagers are now truly cosmic ships, sailing on an interstellar sea, sending back data about an environment never before directly sampled by human technology. Beyond their scientific achievements, the crossing of the heliopause represents a profound milestone in human exploration. The Voyagers have carried human ingenuity beyond the realm of our star's influence and into the broader galactic environment, the first human-made objects to do so. The remarkable longevity of the Voyager spacecraft, designed for a 5-year mission yet still operational after more than 4 decades, stands as one of humanity's greatest engineering achievements. These spacecraft represent technological time capsules continuing to function with computing systems designed in the early 1970s, long before the advent of modern microprocessors and digital technology. At the heart of each Voyager is a computer system with approximately 68 kilobytes of memory, less than a single digital photograph today. The onboard computer, called the Command and Control Subsystem, operates at a speed of 250 kilohertz, making it about 1 million times slower than a modern smartphone. Yet this seemingly primitive system continues to collect data, process commands, and transmit findings across billions of miles of space. The spacecraft's communication system confronts physical limitations that can't be engineered away. Radio signals traveling at the speed of light now take more than 21 hours to reach Voyager 1. This means that any command sent to the spacecraft requires nearly 2 days for confirmation of receipt. If something goes wrong, engineers must deduce the problem, devise a solution, transmit commands, and wait again to see if their fix worked, all while working with decades-old documentation and retired technologies. Both Voyagers transmit data at a mere 160 bits per second, comparable to the earliest home internet modems, but thousands of times slower than modern connections. This trickle of data is captured by NASA's Deep Space Network, a system of massive radio antennas in California, Spain, and Australia. The 70-meter dish antennas are needed to detect the incredibly faint signal, which registers at less than 1/10,000,000th of a watt by the time it reaches Earth. Perhaps the most critical engineering challenge for the Voyager's extended mission has been power management. Each spacecraft carries 3 radioisotope thermoelectric generators that convert heat from the decay of plutonium-238 into electricity. When launched, these RTGs produced approximately 470 watts of electrical power. Today, with the natural decay of their plutonium fuel, they generate less than half that amount. This dwindling power supply has required increasingly strategic management. Since 2007, engineers have been powering down non-essential systems one by one to extend the functional lifetime of the most critical instruments. Heaters for many components have been deactivated, forcing those systems to operate well below their design temperatures. Remarkably, most continue to function despite these extreme conditions. The Voyager's ability to withstand the harsh environment of space for decades speaks to the robust nature of their design. The spacecraft operate in temperatures approaching absolute zero, are bombarded by cosmic radiation, and must maintain precise orientation using thrusters that have fired many thousands of times more than their original design specifications. The most impressive aspect of the Voyager's longevity may be the foresight of their designers. Engineers in the 1970s built in redundant systems, included excess capacity, and designed the spacecraft to be reprogrammable from Earth. This flexibility has allowed mission controllers to upload entirely new flight software, multiple times, teaching old spacecraft new tricks as their mission evolved. Memory management has become particularly challenging as components of the aging computers begin to fail. Engineers have developed creative workarounds, including storing critical data in multiple locations and implementing new data compression techniques to maximize the information returned from each precious transmission. Even the propulsion system demonstrates remarkable engineering. Each Voyager carries 24 hydrazine thrusters for attitude control, maintaining the precise orientation needed to keep their antennas pointed toward Earth. After more than 45 years, the thrusters still function with high precision, though engineers have had to compensate for diminishing fuel pressure and valve degradation over time. The Voyager's durability goes beyond just robust hardware. It's also a triumph of software engineering. The spacecraft operate using a hierarchical fault protection system that can detect anomalies and automatically place the spacecraft in safe mode while awaiting instructions from Earth. This autonomous capability has saved the mission multiple times when unexpected conditions have arisen billions of miles from home. As the Voyager's journey further into interstellar space, they continue to rewrite our understanding of the solar system's outer boundary and the interstellar medium beyond. With diminishing power supplies, mission scientists have made difficult choices about which instruments to keep operational, prioritizing those that provide unique information about this unexplored region. Currently, 5 instrument systems remain active across both spacecraft. The magnetometer, or MAG, measures the strength and direction of the local magnetic field. This has proven crucial for understanding the complex interaction between the Sun's magnetic influence and the interstellar magnetic field. Data from both Voyagers have revealed that the interstellar magnetic field is significantly stronger than predicted and drapes around our heliosphere, creating a complex region scientists call the magnetic highway. The cosmic ray subsystem, or CRS, detects high-energy particles from both inside and outside our solar system. Since crossing the heliopause, both spacecraft have measured a significant increase in galactic cosmic rays, particles accelerated to nearly the speed of light by distant events like supernovae. Simultaneously, they've detected a dramatic decrease in solar energetic particles, confirming their position beyond the Sun's protective bubble. Voyager 2 still operates its plasma science experiment, or PLS, which directly samples charged particles in the surrounding environment. This instrument has revealed that the interstellar plasma is significantly warmer and denser than expected, with temperatures exceeding 40,000 degrees Celsius. Despite this high temperature, the extremely low density means the spacecraft themselves are not in danger of heating damage. The Low-Energy Charged Particle Instrument, or LECP, measures slightly lower energy particles than the CRS and has been critical in establishing the complex energy spectrum of the interstellar medium. These measurements have practical implications for future interstellar missions, helping engineers design appropriate radiation shielding for both electronic systems and potential human travelers. Finally, the plasma wave subsystem, or PWS, continues to detect oscillations in the surrounding plasma. In 2018, this instrument made the surprising discovery of electron plasma oscillations in the interstellar medium, weak vibrations that indicate the presence of shock waves from our sun still detectable beyond the heliopause. These findings suggest that the sun's influence extends far beyond the traditional boundaries of our solar system. Together, these instruments are mapping the structure of our local interstellar environment, the region known as the local interstellar cloud or the local fluff. This cloud, approximately 30 light-years across, contains gas that is slightly warmer and less dense than the surrounding interstellar medium. Understanding its properties helps astronomers piece together the complex history of our galactic neighborhood. One unexpected discovery came in 2019, when Voyager 2 detected an increase in cosmic ray intensity different from what Voyager 1 had encountered at a similar distance. This discrepancy suggests that the heliopause may be irregular in shape or thickness, possibly influenced by the 11-year solar cycle or by differences in the interstellar environment at different locations. The Voyagers have also detected mysterious low-frequency radio emissions that appear to originate from the heliopause itself. These emissions, occurring at frequencies between 2 and 3 kHz, may result from plasma instabilities where the solar wind meets the interstellar medium, but their exact cause remains a subject of active investigation. Perhaps most intriguingly, both spacecraft have detected evidence of what scientists call the hydrogen wall, a region where neutral hydrogen atoms pile up as our heliosphere plows through the interstellar medium. This wall, located just beyond the heliopause, creates a distinct ultraviolet signature that both Voyagers have observed, though neither has yet physically reached this boundary. As the Voyagers continue their outward journey, they are helping to answer fundamental questions about our solar system's movement through the galaxy. Data from both spacecraft suggest that our entire heliosphere may be moving through the interstellar medium at an angle, creating a bow shock ahead of us and a long tail behind, similar to the wake of a ship moving through water. In 2023, scientists analyzing Voyager data made another unexpected discovery. The density of interstellar space appears to be increasing with distance from the Sun. This finding contradicts models that predicted a relatively uniform density in the local interstellar cloud and suggests we may be approaching another boundary or structure within interstellar space. The diminishing power supply on both Voyager spacecraft means their scientific mission will soon come to an end. Current projections suggest that around 2025, power levels will become too low to operate any scientific instruments. By 2030, the spacecraft will likely fall silent altogether, no longer able to communicate with Earth. Yet even as their active mission concludes, the Voyager's journey is just beginning. Moving at speeds of approximately 35,000 miles per hour, both spacecraft will continue their trajectory out of the solar system, racing toward the stars. Voyager 1 is heading generally toward the constellation of Ophiuchus, while Voyager 2 is traveling toward Sagittarius. In about 30,000 years, they will pass through the Oort cloud, the spherical shell of icy objects that marks the outermost boundary of our solar system's gravitational influence, though their instruments will have long since gone silent. The Voyagers carry with them more than just scientific instruments. As we've discussed, each bears a golden record containing sounds and images of Earth, a time capsule of humanity meant to last at least 1 billion years. While the probability of another civilization finding these records is astronomically small, they symbolize humanity's desire to reach beyond our planetary cradle and communicate with the cosmos. Even without an encounter with extraterrestrial intelligence, the Voyagers will serve as silent ambassadors from Earth for the next billions of years. They will outlast human structures on Earth, continuing their journey long after our modern civilization has transformed or perhaps even disappeared. In many ways, they represent humanity's first tentative steps toward becoming an interstellar species. The scientific legacy of the Voyager mission extends far beyond the spacecraft themselves. Data collected by the Voyagers have led to the publication of thousands of scientific papers and have fundamentally reshaped our understanding of the solar system. The discoveries at Jupiter, Saturn, Uranus, and Neptune informed the design and objectives of subsequent missions like Galileo, Cassini, and New Horizons. The Voyager's exploration of the heliosphere and interstellar space has similarly influenced modern missions. NASA's Interstellar Boundary Explorer, or IBEX, launched in 2008, maps the boundary of our solar system from Earth orbit, building on the Voyager's direct measurements. The New Horizons spacecraft, having completed its historic flyby of Pluto in 2015, is now following a similar path outward and may eventually provide additional data points about the heliosphere's edge. Looking further ahead, NASA's Interstellar Mapping and Acceleration Probe, scheduled for launch in 2025, will study how the solar wind interacts with the interstellar medium, directly building on questions raised by the Voyagers. Discoveries and concepts for true interstellar precursor missions, spacecraft designed specifically to probe deeper into interstellar space, are already being studied, with potential launch dates in the 2030s or 40s. Perhaps the most enduring legacy of the Voyager program is how it expanded humanity's cosmic perspective. The famous pale blue dot image, captured by Voyager 1 in 1990 at the request of astronomer Carl Sagan, shows Earth as a tiny point of light, a mote of dust suspended in a sunbeam, from a distance of 6 billion kilometers. This image has become an icon of our planet's fragility and uniqueness. The Voyagers have also demonstrated the remarkable ingenuity and foresight of human engineering. Designed with 1970s technology, these spacecraft have performed well beyond their intended lifespans, adapting to new missions and challenges through creative problem-solving by generations of engineers and scientists. As the Voyager's active mission draws to a close, they leave us with questions as well as answers. Their discoveries about the interstellar medium have raised new puzzles about the structure of our galaxy and our place within it. The mysterious increases in plasma density, unexpected magnetic field configurations, and strange radio emissions all point to an interstellar environment more complex than our models predicted. In the coming decades, new missions will build upon the Voyager's legacy, venturing further into the unexplored regions between stars. But Voyager 1 and 2 will always hold the distinction of being the first, the pioneering spacecraft that carried human ingenuity beyond the boundaries of our solar neighborhood and into the vast cosmic ocean that surrounds us. Though their scientific mission may end soon, the Voyager's journey to the stars is far from over. They will continue their silent voyage through the Milky Way galaxy for eons to come, emissaries of Earth, carrying evidence of a species that looked up at the night sky and decided to explore.